Fusion Mobile, quality e-learning experience on the go.
Fusion Mobile e-learning clinic. My name is Sonya Olaoluwa and I've been walking you through the physics course. We'll be discussing electromagnetic fields and we'll look at the concept of electromagnetism. We'll consider the force on moving charges in the magnetic field. We'll also look at force and field patterns of two current carrying conductors. Then we'll look at currents in loops and coils. Also, application of electromagnetic fields, electromagnetic flux in induction, that in the electric, that's the AC generators, that's the alternating current generators or alternator, then the inductance, and then the transformer, and then the transmission of electricity, and finally the induction coil. So let's begin. So when we're talking about the force on a moving, we've talked about the concepts. So we're talking about the force on a charge in the magnetic field. Of course, we gave the formula the other time. That's F equals to B current L sine theta, or F equals to B V sine theta. You choose the one that is appropriate to the particular situation in which you find yourself. There is also another magnetic property, a magnetic phenomena that was described as the magnetic flux. The magnetic flux is unlike this one, which that is the magnetic flux acting on a singular wire. But what about when it is acting on a region? Of course, we know how magnetic flux is not restricted to a straight line. It is something that happens over a wider area. That's where we come up with the magnetic flux density, which equals BA. The funny thing is, the BA is not restricted to the A because, of course, we know that there would always be a sign because of the nature of the operation of the magnets. So the sign in this place, instead of the angle is in the cosine. That's BA cos theta. So that's what we call is how to calculate the field flux. That is magnetic field. You can calculate the magnetic field strength as BA cos theta. So how do we apply this in circuits? Let's take this question as an example. The question says calculate the force on a charge. The charge is having 2 microcoulombs moving with a velocity of 2 times 10 raised to the power 6 meters per second in a field of magnetic flux in density 0.5 teslas parallel to the field. When we want to solve, of course, we first write out our parameters. We know our Q. Our Q equals plus 2 microcoulombs. We know our velocity. Velocity equals 2 times 10 raised to the power 6 meters per second. And then we know our magnetic flux density. Flux density, that's B, which equals to 0.5 teslas. So we can bring forth our formula. Our formula says F equals to Q BV sine theta. The first one says theta is parallel. When it is parallel, it means theta equals to 0. So if we use the formula, F equals to 2 times 10 raised to the power minus 6 times 2 times 10 raised to the power 6 times our B is 0.5 sine 0. Sine 0 is 0, so automatically everything there becomes 0. So there will be no force, that's 0 newtons. There will be no force acting on it when it is moving perpendicular to the field. But when it is moving parallel to the field rather. But when it is moving perpendicular to the field, theta equals to 90 cos 90 degrees will be formed, and F would now be equal to 2 times 10 raised to the power minus 6. That's our Q. Our B is 0.5. Our V is 2 times 10 raised to the power 6. And sine theta is 90. So this minus 12, if you press all this information into your calculator, your answer will be 2 newtons. Our answer will be 2 newtons. So it is 2 newtons that would be the force acting on the body. Also, in the past, we drew patterns of fields and how they appear. We said, considering the magnetism, we said we have plus and we have minus. If it is plus and minus like this, of course, they are this thing outside all around. Plus always want to give away. Minus also has its own around. Minus wants to receive. So give away and receive, they will connect to each other. They will connect to each other. But in the other profile, where you have plus and plus or minus and minus, this one wants to give away. This one also wants to give away. So they can't fuse into each other. So they will repel one another. They will repel one another. So that's what the field diagrams look like. But what is the force of attraction that exists between two coils that are moving that are carrying currents? What's the force of attraction? Well, the attraction between them can be calculated as F over L equals to mu I1 I2 divided by 2 pi r. I'll take it again. The force of attraction between them can be given as, per unit length, can be given as F over L equals to mu I1 I2 divided by 2 pi r, where r is the distance between them. Of course, each of them has a kind of area. Now, this is the length of the length of the conductors. Of course, mu here is permeability of vacuum. That's what our mu there represents. It represents the permeability of vacuum. All right. let's look at currents in loops and coils. Currents in loops and coils. The first thing to bear in mind when you want to talk about currents in loops and coils, we should consider what is torque. What is torque? Torque is a kind of force that's the turning force. The turning force. Of course, we will talk about torques and couples. So, how do we calculate torque? Torque is calculated as our torque is calculated as IAB sine phi. IAB sine phi, where I is the current in the system, A is the area of the magnetic field or the magnetic field, yes. B is the magnetic field intensity, and sine, the theta there, phi there rather, the phi there considers the angle formed by the current in relation to the magnetic field. The current in relation to the magnetic field. There should be an angle between them. So that's what tell us what our phi. Yes, our phi is the angle between the current and the magnetic field. When phi is at 90 degrees, then the system will be at maximum, and when phi is at 0, it will be at the minimum. So, but it should also be noted that earlier we talked about. Okay, let's leave that. Yes, at different points in the loop. At different points in the loop, that's in the operation of the electromagnetic device. Of course, for every when you are passing current through an electromagnetic device, you're going to expect a turning effect. Yes, you'd expect a turning effect. A very good example of a device, an electromagnetic device, which has electric current being passed through it, is our electric fan, or generally electric motors. When you pass electricity through an electric motor, it creates a turning effect, and it is that turning effect that is described by the torque. Now, the overall force of the system should always be equal to 0. Now, the entire force in the system should be equal to 0, which means at different points in time there will be varying forces, but when you resolve them all together, your outcome would be. You're using a selenium coil for the production of your electromagnets. Of course, we know that our selenium coil creates temporary magnets. When you're using your selenium coil for the production of your electromagnets, then your B can be calculated as NL mu NL, where mu, of course, remains permeability of vacuum. N is number of turns, and L is length of the selenium coil. Permeability of vacuum, number of turn, and length of the selenium coil. It should also be noted that the permeability of vacuum equals 4 times 10 raised to the power 6 A. Sorry, 7 AM. 4 times 10 raised to the power 7. It should also be noted that our permeability of vacuum equals 4 times 10 raised to the power 7 AM. That's amperes per meter. 4 times 10 raised to the power minus 7 amperes per meter. So these are some basic formulas we should keep at hand for use sometime soon. Okay, what are the applications in which we find electromechanical fields? What are the applications in which we find electromechanical fields? I've mentioned some of them. We use electromechanical fields in our electric motors, not only in our electric motors, we use them in the operation of some machines, both simple and complex. Machines like the gong bell, there's electric, we'll use electromagnetic fields. Also in the production of our generators, electricity generators, we use electromagnetic fields. Also in the making of some apparatus, instruments, that's called instrumentation. In making of some instruments, we still use our electromagnetic field, the knowledge of our electromagnetic field, find their application. Electromagnetic flux induction. To discuss electromagnetic flux induction, there are some things that we need to know, some laws that we need to understand, that we need to have at heart. On your screen now, you'll be seeing some of the laws that are being displayed. The first of them is the Faraday's law. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction states that whenever there is a change in magnetic flux linked with a circuit, an electromotive force, which is EMF, E, is induced, the strength of which is proportional to the rate of change of flux. An electromagnetic flux is induced, the strength of which is directly proportional to the rate of change of flux. So, the expression for that is what we have here. It says it is is directly proportional to that. Let's just keep that in mind. Let's choose another law and let's assess that also. We have the Lenz's law. The Lenz's law says that the direction of the EMF induced is such that it opposes the change that produces it. So this law stands to establish the law of the conservation of energy. And also we have the Fermi's right-hand rule. The Fermi's right-hand rule. The Fermi's right-hand rule says if the thumb and two fingers are held at right angle to each other, the first finger points in the direction of the magnetic field, the thumb points in the direction of the motion, while the second finger points in the direction of the current. So it's saying something like this. So while the direction of the magnetic field, that's the first finger, is pointing, the direction of the current is pointed down, and direction of the motion goes to the thumb. So that's what the Fermi's rule states. So basically we have to work with this, and this results to E equals minus the phi dt minus the phi dt. So when we try to simplify further, that is when there is just a singular turn. But when we have multiple turns, then we know, of course, we have to modify. We have to modify and introduce E and turn the equation into equals to d dt. Of course, where our n is number of turns of coil, the number of the turns of coil, number of the turns of coil. And of course, we know that our file is the same thing as BA cos theta. BA cos theta. So we can bring in the BA cos theta, and when we relate A and when we bring it into the expression, we would have our final answer to be EMF, that's E, equals to N mu EMF will be equals to, that's E will be equal to B N mu sine theta. Bm omega sine theta. Sorry. E with MF will be equal to so EMF will be the current E will be equal to E will be equal to BAN mu sine T sine T. One more time. E would then be equal to BAN mu sine T. So this is the expression that is used to calculate the amount of electromagnetic induction that is being produced. Of course, that induction is actually the EMF that is produced, and of course EMF is maximum when mu equals 90. When theta equals 90. So we'll have the short form of this particular expression to simply be EMF, that's maximum EMF, will be equal to BAN mu. That will be our maximum possible EMF that will be induced. So let's try to explain what happens, how we generate electricity from our magnetic fields or inside our alternators. What really happens? Well, we have in the generator we have two bars of magnets. One is the north, one is the south, and in between them we have the armature. The armature contains several windings of coils, induction coils, which are then connected by carbon brushes. Now, as this thing turns, there's a brush there, there's another brush here. As the armature is being turned, of course there are several windings, let's say n number of windings in it. As the armature turns, the electricity is being induced inside the coils. So those electricity that are induced inside the coils are taken in by the carbon brushes, which are connected to the rings, from the rings to the carbon brushes, and they can be taken out and measured. Of course, you can take it out and put your ammeter or put a galvanometer there. You can take the measurement and you can use it to connect to whatever circuit. That's how electricity is being generated. Now, if you take note of something, I'm having two brushes and they are full. But if it is in the direct current, we don't have the full brushes, we only have half brushes, two half brushes, so that electricity breaks in production. We only have two half brushes, so that the electricity breaks in production. And in this particular case, we have DC being produced and not alternating currents. That's the basic difference between your DC generator and your AC generator. While your AC generator has a waveform, your AC generator has a waveform like this, EMF and time in seconds, EMF in volts. That's a waveform of this, something like this. This is what your AC generator produces, but your DC generator has something like this. It only produces along one side of the diagram. So your AC produces in both directions, that is up and down. Your DC only produces in one particular direction. Okay, let's talk about inductance. Inductance. When we are talking about inductance, what do we mean? Inductance is simply the inductance of a system is a kind of resistance that the system creates in opposition to the flow of current. We have two kinds of inductions. Two kinds of inductions. We have the self-induction and the mutual induction. In self-induction, a coil starts to produce the EMF by itself. It produces the EMF by itself, not being affected by another coil. The EMF produced in this particular coil can be calculated as EMF equals to, or the energy stored, EMF equals to, the EMF produced in this coil can be calculated as EMF equals to L, the I dt, where the L is the inductance, the I dt is rate of change of current, that's the EMF. And of course, the work done by this particular induction can also be calculated as work or energy stored as half Li squared. Half Li squared. Induction is tied to currents. Induction is tied very much to currents. Also, the other type of induction, as said earlier, is the mutual induction. Mutual induction. In mutual induction, an induction coil initiates the induction in another material. An induction coil initiates induction in another material, and mutual induction, the EMF produced is calculated as that's mutual induction. But this M is given as the mu, which is the permeability of vacuum multiplied by the area, that is the area of their interactions, multiplied by the number of coils of the primary and number of coils of the secondary, divided by the length of the coils. So you can put this into this expression and you can get your EMF that will be produced. Of course, you first calculate this and you bring the answer into that other one. Maybe EMF in 1 would be equal to L1 multiplied by dL2 over dt. Sorry, let me verify it. That is, EMF in 1 equals to L1 dL2 over dt, and EMF in L2 will be L2 dL1 over dt. Of course, the M at this point can be calculated as the square root of L1 L2. Now, it is the knowledge of induction that was used in the development of transformers. Covered inductance. The knowledge of induction finds its use in the development of transformers. A transformer is an electronic device that either steps down or steps up electrical power. Electrical voltage, rather, not power. It steps up or steps down electrical voltage. Of course, it uses the knowledge of mutual induction. What does it do? How do they do it? They have certain number of coils. They coil two sets of coils and bring them close to each other, or sometimes in contact with each other. Not in contact, but partially in contact with each other, very close to each other. How is this done? What does this do? The primary coils will be wound, and secondary coils will also be wound. Now these two coils, when you talk about the primary coils, is the one that is bringing in the electricity, and secondary coils is the one that is about to take out the electricity. So the amount of power, the power within the system remains the same, but when voltage reduces, current increases, and when current increases, voltage reduces. So for calculating within a transformer, calculations involving transformer, we just need to bear in mind number of turns of the primary coil divided by number of turns for the secondary coil equals to voltage across the primary coil divided by voltage across the secondary coil, which equals to current flowing in the secondary coil divided by current flowing in the primary coil. All the others are following primary, secondary, but current alternates. Current begs to differ. In other words, when current is high, voltage is low. When voltage is high, current is low. Let's take an example on transformers. Let's take a question on transformers. A transformer which can produce 12 volts from 22 volts, that is I don't know what's distracting. Let's take this question on transformers. A transformer can produce 12 volts from a 22 volts, that's RMS, that's root mean squared supply, has an efficiency of 80%. If the current in the secondary is 10 amperes, calculate the current in the primary. Of course, they said it can produce 12 from 220. So it means our primary volts, as VP, is 220 volts, and our secondary VS is 12 volts. Our secondary current IS equals 10 amperes. We're not told the number of turns, but we know that efficiency, that's efficiency of any circuit, would be equal to inputs over outputs multiplied by 100%. And input here is power, and our power is calculated as VI. So we can say input, that is primary, output over inputs, rather, not input over outputs, outputs over inputs. So our output, which is secondary, which is this times this, this is this times this, yes, that's 12 times 10 divided by 220 times x, which you don't know, multiplied by 100, should give us 80%. That's 80%, yes, should give us 80. So that's efficiency. We're told our efficiency equals 80%. Efficiency equals 80%. So solving mathematically, we'll have up here 0 cancel out 0. (1200) over 22x equals to 80. So x will equal to 1200 divided by 22 multiplied by 80. When we enter the information into the calculator, we'll get 0.68 amperes. So that's the amount of current that is provided by the primary coils. That's the amount of current that is provided by the primary coils. We'll quickly talk about transmission of electricity. Transmission of electricity. So how is electricity being transmitted? Electricity is transmitted at high voltage and not at high current. Electricity is transmitted at high voltage and not at high current. When electricity is about to be produced, it is produced at about 2,500, or it's produced within 2,503. Electric generator has the capacity of producing up to 250,000 volts of electricity, but this electricity is further stepped up into to about 4,000 volts, 400 kilovolts of electricity. That is, it is being stepped higher instead of it being transmitted at that point. Why? Because power remains constant, and if you're transmitting at low voltage, your chances of power losses is reduced. That is, power losses due to heating is reduced, as against when you transmit via electric current. So when you transmit at high voltage to beat or minimize energy losses. And of course, a step down transformer will be introduced to bring it back after transmission. Okay, let's talk about induction coil. The induction coil. The induction coil is a device which enables us to obtain high EMF from low voltage systems. It enables us to get high voltage, high EMF from low voltage, from low direct entry and direct current voltage. It produces a frequency. It is also known as a frequency generator. Yes, it's also known as. It is found mostly in the ignition systems of vehicles. Your vehicle actually needs a very high electrical current to start work, but your induction coil summons this and puts everything to work. It brings up the amount of electric current that is needed to start your vehicle. In this particular topic, we have considered the electromagnetic fields, and we talked about the concept of electromagnetism. We looked at the force on a moving charge. We considered the force and field patterns of two currents carrying conductors. We also looked at currents in loops and coils. We talked about the application of electromagnetic fields, electromagnetic field flux induction. We looked at generators, inductance, transformers, also the transmission of electricity and the induction coil. In a few seconds, some questions will be displayed on your screen. Please answer them, and if there is any part of this lesson which you do not understand, you can go over the video one more time for better clarity. Thank you.